There is a common assumption that automating tasks on the web is as simple as connecting a large language model to a browser. In a live production environment, that naive approach falls apart. Unrestricted agents rapidly burn through session memory and exhaust expensive API quotas on unusable junk data. A single, unconstrained script trying to process complex, multi-page web architectures will inevitably lock up and crash. This documentation shows the alternative, a multi-agent architecture explicitly engineered to handle the exact constraints of the modern web. To prevent system lockups, the system physically separates pure data discovery from actual browser execution. True agentic automation relies heavily on strict state management and engineering for graceful degradation. Two agents must drive the exact same Edge browser session on port 9223, forcing the second to wait until the first exits. By contrast, a third agent touches no browser at all. Because it is headless, it runs concurrently without competing for the port. The first discovery module, Agent 1A, relies entirely on an API pipeline. It operates under a strict 20-minute execution ceiling. Without that ceiling, a single infinite loop would consume the entire session, and the downstream platforms queued behind it would never run. The external environment imposes its own limits. Take the target site Nowcrete, which sits behind an Akamai bot wall. If you inject a standard fetch command, the site immediately returns a recapture required error. The request fails because it lacks the specific sensor data generated by the site's own JavaScript. The engineering workaround abandons forging the call entirely. The agent navigates to the search page, lets the browser execute the native JavaScript to make an authentic request, and then intercepts the clean response directly off the network wire. A resilient system survives by hijacking the native behavior of the host environment. This funnel illustrates the cheapest check first logic. Expensive tasks happen last. Gate 1 drops duplicates via MD5 hash. Gate 2 enforces one application per company daily. Gate 5 drops mismatched tech stacks via regex. Gate 6 calculates a deterministic fit score, bypassing external APIs. Because this calculation requires no model, the pipeline continues to process, filter, and score leads, even if the daily token budget is exhausted. System scalability requires ensuring that an expensive LLM is only ever exposed to highly qualified, heavily sanitized data. Unchecked browser automation carries severe hardware risks. Early runs of the system left over 60 tabs open simultaneously, slowing the host machine to a complete crawl. Now, after every single job, the system aggressively sweeps the browser back down to a strict 4-tab limit. This documentation details how the system handles unstructured data entry. When confronted with application questions, it relies on a rigid 3-tier hierarchy. First, it applies hard-coded rules for common fields. Second, it searches a local cache of successful prior answers. The generative model is strictly the last resort. This chart outlines the model cascade. Relying on one AI provider guarantees failure. Here, Grok is exhausted, Gemini is over quota, and Allama is unresponsive. The system parses exact error codes for precise recovery, resting the exact required duration instead of burning non-existent quota. If the Grok model rejects its own output by wrapping the JSON in markdown fences, a strict validator catches the error and strips the syntax. Proper error recovery requires parsing the specific failure state. A timeout demands a completely different protocol. The final challenge for the pipeline is verification. The system must distinguish between an application that genuinely failed and one that simply executed without triggering an on-screen confirmation. A true failed state means the form never opened, the wizard became permanently stuck, or the apply button simply did not exist. This is entirely different from an awaiting review state, where the data was submitted, but the parser couldn't locate a definitive success message on the resulting page. Treating awaiting review as a failure is dangerous. Retrying that job forces the pipeline to submit a duplicate, overlapping application. For verification, the third agent acts as a passive inbox scanner. Reading an email receipt, it automatically flips the database status from awaiting review to applied. It reads and classifies incoming replies, sorting interviews, rejections, and receipts to definitively prove a transaction cleared. Previously, correcting these ambiguous database rows required a human auditor to read the logs and update the failures by hand. High-reliability autonomous agents prioritize precise error trapping and external state verification over raw generative capability.